Welcome back to the deep dive. You know the drill. We take that overwhelming stack of sources, articles, and research, and we distill it down into the core knowledge you need.
And if you've been following the world of large language models, it feels less like progress and more like
Yeah.
a high-stakes arms race, right?
Exactly. Every quarter there's a new model, a bigger model, but the cost, the sheer difficulty of scaling these things, it's becoming prohibitive.
We're hitting a wall, a serious one.
So that brings us to the central question for this deep dive. Instead of pouring all these resources into one giant single brain, what if we just made the smart models we already have work together?
That's the perfect way to frame it. And that's our mission today. We're going to unpack the research behind a new approach called mixture of agents, or MOE for short.
MOE.
It's this layered collaborative system. It leverages the collective know-how of multiple LLMs to iteratively refine an answer and the results. That they really are pushing the boundaries.
And here's the thing that just stopped me in my tracks. The reason you have to pay attention to this MOE approach, using only existing open source LLMs.
The ones anyone can get their hands on.
It recently surpassed GPT-4 Omni, the reigning commercial gold standard, on a leading benchmark.
The comparison is pretty striking. On AlpaCaIVol 2.0, which is all about measuring alignment with human preferences, the open source MOE collective, it scored a 65.1%.
And GPT-4 Omni.
57.5%. And that's not a small margin. That's a decisive gap. It proves that this kind of collective orchestrated intelligence can now outperform the biggest single models out there.
Okay, that completely shifts the paradigm. So let's unpack this. What's the foundational principle? It hinges on something the researchers call collaborativeness.
Right. So the core finding, the thing that really kickstarts this whole idea is an individual LLM just generates a better response when it sees what other models have produced first.
Like as auxiliary information.
Exactly. They just make better decisions when they get to review a few different drafts before producing their final answer.
But here's the part that feels really counterintuitive to me. You'd think this only works if the other answers are, high quality, good examples.
You would think.
But the research found the improvement happens even when the other responses are lower quality than what the model could have done on its own.
That is the key finding. It's what separates MOE from just, basic ensemble methods. The value isn't getting a perfect answer to copy. It's about processing diverse perspectives, even flawed ones, and using them to trigger a stronger synthesis.
So the diversity of the input is actually more important than the quality of every single one of those inputs.
That's it. When you look at the data for models like Qwen, Mixtral, Llama, all of them showed these significant jumps in their win rate when they were given external responses to consider first. It's almost like the bad suggestions clarify what not to do.
Like guardrails.
Precisely. It's like a brainstorming session. You ask 3 people for their ideas. One is brilliant, one is flawed, one is just partial. Your own final idea is stronger because you've seen all 3. You've anticipated the problems from the flawed one.
Okay, so that multiple perspective input is the fuel. Let's move to the engine. Walk me through the actual structure. How did they build this mixture of agent system? It sounds like an assembly line.
That assembly line metaphor is spot on. It's a layered system for iterative refinement. So layer 1, multiple LLMs, the agents, independently generate their first responses to the prompt. These are the proposers.
Just generating a bunch of different options.
A diverse set of options, yeah. Then the magic happens. The process moves to the next layer. An agent in this layer takes all those raw outputs from layer 1 and uses them as input. Its job is to synthesize a new, better response from all that.
And that's the iterative part. It can happen multiple times.
It can. The default setup in the research use 3 layers. So it's refine, then refine again.
But this whole thing falls apart if they just mash the answers together. The output would be a mess. What are the actual instructions for these aggregator models?
That's the critical piece. It's called the aggregate and synthesize prompt. And it explicitly tells the model, your job is not to copy. Your job is to critically evaluate, find biases, resolve conflicts, and only then offer a refined, accurate, comprehensive reply.
So critical thinking is baked right into the process.
Exactly.
Now, when I hear mixture of agents, I immediately think mixture of experts, MOE. We need to be clear here. What's the difference?
It's a great question, but they operate on totally different levels. MOE works internally, inside a single, massive model. It has specialized subnetworks or experts, and a routing layer sends parts of the problem to them. It's like deep engineering of the model itself.
Like surgery on the LLM's brain.
A perfect analogy.
Yeah.
MOE, on the other hand, is all external. It works at the model level. It takes multiple full off-the-shelf LLMs and just orchestrates them through the prompt.
Which means?
No fine-tuning. Zero. You can plug in the newest open-source model tomorrow. It's incredibly flexible.
That flexibility is huge. Okay, let's circle back to performance. We know it beat GPT-4 Omni on Alpha-Eval 2.0. Remind us why that benchmark is such a big deal.
Alpha-Eval 2.0 is respected because it's built to measure alignment with what humans actually prefer. But its secret sauce is that it controls for length. So many models cheat by just being long-winded.
Right, they just produce these huge walls of text.
Exactly. Alpha-Eval neutralizes that bias, so you're measuring real quality, not just word count. And get this, the MOE version that used GPT-4 Omni just as the final aggregator.
So as the last editor in the assembly line.
Right. It got the absolute highest score overall, 65.7%.
So even the best single model is better when it's part of the team. We also have data from the Felle score evaluation, which is much more granular. Where did MOE really shine there?
It excelled where single models can be a bit shaky. It showed huge improvements in robustness, correctness, factuality, common sense, insightfulness, and completeness.
So all the things you want for a really reliable answer.
It validates the whole hypothesis. The collaboration acts as a serious quality control check.
But there's always a trade-off. What did Flesk reveal as the downside?
The one metric where MOE performed worse was conciseness.
I was going to guess that.
Yeah. I mean, it makes sense. The final aggregator's job is to synthesize everything, so the output tends to be a bit more verbose. It's the cost of being thorough. But it's not just chat. MOE also boosted accuracy by a lot on complex math reasoning tasks, so it's not just for refining conversations.
Let's dig into why that aggregation is so good. Is it really sophisticated synthesis, or is it just a clever way to pick the best answer from the initial group?
It's absolutely synthesis. They tested this. They ran a baseline called an LLM ranker, where the model just had to pick the single best answer. No combining, no refining. MOE blew it out of the water. The benefit comes from the aggregator intelligently weaving together the strongest parts from all the proposals.
So if diversity is the key, how important is it that the models are actually different? I mean, could you just get 5 slightly different answers from the same LLM?
Great question. And no, diversity of the source is essential. They compared a single proposer setting one model multiple tries against a multiple proposer setting with different LLMs.
And the multiple proposers were better.
Consistently better. You need different model DNA, different training, different architectures, not just one model trying to sound different 5 times.
This suggests we're moving toward building, like, an optimal roster. Did the research show that some LLMs are just better at certain jobs?
They absolutely did. They found models naturally specialized. Some are great proposers. They generate diverse, useful ideas. Others are better aggregators. They're great at synthesizing all those inputs into one high-quality output.
Was there a specific example that stood out?
Yeah, a really clear one. Many of the top models like GPT-4o and Llama-3 were good at both.
Yeah.
Wizard LM 8x22b was an excellent proposer.
Yeah.
Generated fantastic source material.
Yeah.
But when they made it the final aggregator, its performance dropped. It struggled to be effective in that role.
That's fascinating. It's like having a brilliant creative who comes up with 10 amazing ideas, but you would never ask them to write the final polished report. You need a dedicated editor for that.
It proves you could optimize these MOE teams by assigning roles based on a model's inherent strengths. We're talking about managing AI talent pools now.
I want to touch on how robust this is. There was a case study where none of the initial proposals were good. Like, they were all terrible. What happened then?
This might be the best example of MOE's power. Even with a terrible starting point, the aggregators successfully identified and pulled out the few good, accurate details scattered across those otherwise awful responses.
So it salvaged something useful from the wreckage.
Exactly. It synthesized a final answer that was measurably better than any of the single bad proposals it was given. It wasn't a perfect answer, but it showed the mechanism is robust enough to work with even low-quality inputs.
Okay, this sounds incredible for quality, but we have to talk about the economics. Is this just exponentially more expensive? You're running all these models in layers?
It brings us to the budget analysis, which is critical. The researchers put MOE right on the Pareto front.
For our listeners, what does Pareto front mean here?
It means it's on that optimal curve where you get the most performance bang for your compute buck. And to prove it, they created a cost-effective version called MOE Lite.
MOE Lite. What did they change?
They cut it down to just 2 layers and used a more efficient aggregator.
But doesn't cutting layers dilute the whole point? The iterative refinement?
You'd think so, but the quality loss was minimal, and the cost reduction was massive. Moe Lite still outperformed GPT-4 Omni, and it beat GPT-4 Turbo by about 4%, while being more than twice as cost-effective.
So it's better quality for less than half the price.
It's genuinely close to that holy grail of AI development.
We've covered cost. So what's the big catch? What's the technical hurdle stopping this from being everywhere tomorrow?
The main practical limitation is latency, specifically time to first token, or TTFT.
The wait time before you see the first word appear?
Exactly. Because the process is serial layer 1 has to finish before layer 2 can start. The user feels that delay. You can't start outputting the final answer until it's gone through the whole pipeline.
Which hurts the user experience, especially for real-time chat. Does Moe Lite help with that too?
It helps a lot. Fewer layers means less of a delay. That's the main strategy right now.
Right.
But people are also looking at things like chunk-wise aggregation, where it synthesizes in segments to get the text flowing sooner.
So this whole deep dive really feels like it's shifted the conversation. The core takeaway, for me at least, is that the future of AI capability isn't necessarily about building one bigger, more expensive model.
I think that's right. The paradigm is shifting toward designing these intelligent, collaborative teams of existing models. For you, the listener, it shows that this kind of multi-step collaboration, even with imperfect parts, is an incredibly powerful way to generate reliable, high-quality knowledge.
And that leads us to our final provocative thought. We've seen that Moe gets better with more layers and more diversity. The research suggests that performance just keeps improving as you add more diverse agents. So, if cost and latency were no object, how many unique specialized agents would it take to create a collective capable of solving, say, any problem? 100, 1,000.
Something to chew on. Thanks for joining us for the deep dive.
We'll see you next time.